Welcome to G Fun Facts Online. Today, we are heading into the vast, frozen expanses of the circumpolar north to discuss a phenomenon that sounds like science fiction, but is an alarming ecological reality. We are talking about zombie fires. These are the remnants of summer infernos that simply refuse to die. Instead of extinguishing under the crushing weight of winter snow and sub-zero temperatures, these fires burrow deep into the organic soil. They enter a state of flameless, persistent combustion, hibernating through the dark months fueled by ancient carbon, only to re-emerge in the spring, fully formed and ready to ignite the landscape all over again. To the casual observer, the idea of fire surviving beneath a meter of snow seems to defy the laws of physics. We know that fire requires heat, fuel, and oxygen, three elements that the frozen Arctic winter appears to systematically deny. Yet, the science of smoldering peat reveals a complex interplay of thermodynamics, biochemistry, and geology that allows these undead fires to not only survive, but thrive in conditions that would snuff out a conventional flame in seconds. As the Arctic warms at a rate nearly 4 times the global average, zombie fires have transformed from a rare ecological curiosity into a significant climate feedback mechanism. They are no longer just anomalies, they are a symptom of a biosphere in transition. In this episode, we are going to delve deep into the molecular, ecological, and atmospheric mechanics of zombie fires, exploring how microscopic bacteria can ignite a landscape, how ancient indigenous wisdom predicted this crisis, and why the sleeping giants of the carbon cycle are waking up. Let us begin with the anatomy of the undead, specifically, the physics of smoldering. To understand a zombie fire, you first have to discard the traditional image of a wildfire. When we think of a forest fire, we typically visualize a flaming front, consuming the canopy and underbrush with high heat and visible flames. This is called flaming combustion, a gas phase reaction where volatile gases released by heated fuel mix with oxygen and ignite. Zombie fires, however, rely on a fundamentally different process known as smoldering combustion. Smoldering is a heterogeneous surface combustion process. It occurs when oxygen directly attacks the surface of a solid fuel without the intermediate step of a gas phase flame. It is the exact same physics that keeps a cigarette burning or charcoal glowing in a barbecue. The temperature differential is key here. While flaming fires burn at temperatures between 1500 and 1800 degrees Celsius, smoldering fires burn at significantly lower temperatures, typically between 400 and 600 degrees. They are also incredibly slow. Flaming fires race across the landscape, driven by wind and convection, but smoldering fires creep. They move at a glacial pace, often advancing only half a meter to 5 meters per week. But this slowness is deceptive. It allows the fire to be incredibly thorough, consuming not just the surface vegetation but the soil itself. You might wonder how this survives the winter. The survival of these fires is a paradox of insulation. Snow, often seen as the enemy of fire, actually acts as its protector. Fresh snow consists of ice crystals trapping pockets of air, making it an exceptional thermal insulator. This creates what we call the igloo effect. When a peat fire burns deep into the ground, it creates a cavity of heat. If a heavy snowpack falls early in the season, it traps this heat underground. The soil temperature can remain at a cozy combustion point, while the air temperature, just a few feet above, drops to -40. As for oxygen, peat is porous. Even under snow, the network of pores within the dried organic soil allows oxygen to diffuse slowly to the combustion front. The fire does not need a gale of wind. It needs only a whisper of oxygen to maintain its slow oxidation. The fuel here is peat, which is not just dirt. It is a matrix of partially decayed organic matter, mosses, sedges, and shrubs that has accumulated over thousands of years. In the Arctic, the cold slows decomposition, meaning carbon is stored rather than released. A single meter of peat can represent a millennium of carbon sequestration. When a zombie fire burns, it is not burning wood. It is burning the history of the ecosystem itself. Now let us move to the spark of life. One of the most fascinating frontiers in this field is the mechanism of biological self-heating. While many zombie fires are remnants of lightning strikes, recent research suggests that some may start or be sustained by the microscopic life teeming within the soil. This is the microbial heater. In the initial stages of peat decomposition, biological activity plays a crucial role. Bacteria and fungi break down organic matter, a metabolic process that releases heat. Mesophilic bacteria, those that thrive at moderate temperatures, can raise the temperature of a peat pile to about 40 degrees Celsius. As the temperature climbs, thermophilic, or heat-loving bacteria, take over, pushing the temperature up to roughly 60 or 70 degrees. But biology has a limit. Most bacteria cannot survive above 75 degrees. However, at this critical temperature threshold, the peat enters a state of high chemical reactivity. The heat generated by the dying microbes is sufficient to trigger low-temperature chemical oxidation. This is the handoff, where biology ends and physics takes over. The heat generated by chemical oxidation then drives the temperature up to the smoldering ignition point, which is over 200 degrees, creating a fire without a spark. Recent studies have even highlighted specific bacterial agents, such as Pseudomonas taiwanensis, which have been observed accelerating the decomposition of peat fibers. While not solely responsible for fire, these decomposers create the heat preload necessary for ignition. Furthermore, methanogens deep in the anaerobic layers produce methane. As the fire dries the soil, this methane can seep upward, providing a highly flammable, volatile fuel that aids the transition from smoldering to flaming when the fire breaches the surface. At the molecular level, this gets even more complex with the chromophore effect. The decomposition of organic material produces chromophores, compounds with conjugated carbon-carbon double bonds that absorb light and energy. Research indicates that the breakdown of these compounds can generate singlet oxygen, a highly reactive form of oxygen. This singlet oxygen attacks the carbon structure, creating hydroxyl and peroxyl radicals. These radical reactions are highly exothermic, meaning they release heat. In the dense, insulated environment of a deep peat layer, this heat cannot escape. It accumulates until the carbon structure begins to char and eventually smolder. So why is this happening now? Zombie fires are not new to the planet, but their frequency and intensity in the Arctic are unprecedented in the modern record. We must look at the changing geology and hydrology of the North. Essentially, we are seeing the drying of the sponge. Healthy peatlands are wet, often called mires or bogs, and are naturally resistant to fire. They act as sponges, holding water tables high. However, climate change is drying this sponge out. As Arctic air temperatures rise, the vapor pressure deficit increases. This draws water out of the soil at accelerated rates. Simultaneously, permafrost acts as an impermeable barrier that holds water near the surface. As permafrost thaws, this floor drops out. Water drains deeper into the ground, leaving the surface peat dry, aerated, and perfectly primed for deep burning. Paleoecological studies using peat cores from Alaska and Siberia reveal that for the last 3,000 years, fire was a relatively rare event in the high tundra. But starting around 1950, and accelerating dramatically after the year 2000, the frequency of fires has spiked to levels unseen in the Holocene record. We are entering a Pyrrhic transition, a shift from a climate-limited fire regime where it was too cold and wet to burn, to a fuel-limited regime where it burns until it runs out of fuel. We have seen this in action. In Siberia, between 2019 and 2020, satellite data tracked massive wildfires that went dark in October, only to reappear in the exact same coordinates in May. These were not new fires. They were the previous year's fires waking up. This proved that overwintering fires could account for up to 38% of the total burned area in some years. Similarly, the Donny Creek Fire in Canada, one of the largest in British Columbia's history, had parts that overwintered, surviving temperatures of -40 degrees to re-emerge the following spring. It is important to note that while Western science has only recently focused its satellites on this, indigenous peoples of the North have lived with them for millennia. Communities such as the Gwich'in and Athabascan peoples have long had terminology for holdover fires. Traditional knowledge holders have described seeing steam rising from the ground in deep winter, or smelling smoke when there was no lightning. Historically, indigenous fire management played a role in mitigating these risks. Practices often involved controlled burns in the early spring, when the ground was still frozen but the grass was dry. These cold burns removed the surface fuel without heating the underlying peat. However, colonial fire suppression policies outlawed these practices, allowing fuel loads to build up for a century, creating the fuel powder keg that now feeds these intense, deep-burning fires. This leads us to the vicious cycle of climate feedback loops. The most alarming aspect of zombie fires is the carbon bomb. Peatlands cover only 3% of the Earth's land surface, but store twice as much carbon as all the world's forests combined. When a zombie fire burns peat, it releases old carbon, sequestrated over millennia, unlike the young carbon released by burning trees. Standard emissions models often miss this, calculating carbon release based only on surface vegetation. Some estimates suggest smoldering peat fires contribute an additional 15% to global fire emissions currently unaccounted for. Then there is the albedo effect. Zombie fires re-emerge in spring when snow is still on the ground. The smoke they release is rich in black carbon, or soot. When this black soot settles on white snow and ice, it darkens the surface, reducing its reflectivity. The dark snow absorbs more sunlight and melts faster, exposing more peat to drying and warming, increasing the risk of more fires. Additionally, the heat from a smoldering fire goes down, degrading the permafrost. This causes the ground to collapse into thermokarst sinkholes, which can drain water away or create anaerobic pools that release methane. Detecting these fires is a massive technological challenge. You cannot fight a fire you cannot see, and detecting a fire burning 2 meters underground is difficult. Standard satellites rely on high thermal signatures of open flames, but smoldering fires are relatively cool. Scientists are now developing algorithms using high-resolution optical imagery to spot early wake-up fires, looking for smoke plumes in early May. They are also using synthetic aperture radar to detect subtle changes in ground texture and moisture caused by underground heat, known as thermal inertia. On the ground, detection involves looking for fumaroles, vents where smoke and steam escape the earth. The future likely involves drones equipped with multispectral sensors to detect the specific chemical signature of peat smoke. Finally, how do we fight the unfightable? Extinguishing a zombie fire is a logistical nightmare. You cannot simply spray water on it. The water will evaporate or channel through cracks, missing the fire. This is the peat soup problem. To put out a peat fire with water, you essentially have to turn the landscape into a bog again, requiring millions of liters of water, which is often impossible in remote locations. However, recent research from Imperial College London suggests that adding surfactants or wetting agents to water can reduce the amount needed by 40%. These agents break the surface tension of the peat, which becomes hydrophobic when dry, allowing water to penetrate the microscopic pores. If water is not an option, we turn to compression and trenching. Heavy machinery is used to compress the soil, closing pore spaces and cutting off oxygen. Or, crews dig trenches down to the mineral soil to create a physical barrier. But the only long-term solution is ecosystem restoration. Re-wetting the landscape by blocking drainage canals and reintroducing beavers can raise the water table, because a wet peatland is a fire-proof peatland. In conclusion, zombie fires are a warning. They are a signal that the Arctic's resilience is eroding. The fire that will not die is a potent metaphor for the climate crisis itself, a problem that persists, festers, and re-emerges with greater intensity if ignored. Addressing this requires a fusion of high-tech satellite algorithms and biodegradable suppression agents. Alongside the reinstatement of indigenous land stewardship, we must view the ground beneath our feet not as inert dirt, but as a living, breathing, and potentially burning volatility. The zombies are waking up. The question is whether we will wake up in time to stop them. Thank you for listening to G Fun Facts Online.